Again, this is pretty deep into the linear algebra course, but it's one of the most important topics, and to me, one of the most fun things to do in linear algebra. Like when you have nothing else to do and you're at home alone, you know, construct some matrix and find the eigenvalues and eigenvectors for that particular matrix. You'll have the time of your life, trust me. So in this particular video, we're just going to kind of define what an eigenvalue and eigenvector is, and we're going to show you how to find eigenvectors and eigenvalues, and we'll do several examples of finding eigenvalues and eigenvectors. So let's get the show going.
Specialized in science and math, original black men, busting thoughts that pierce your mental, the fierce, ripping your section, vocal toe-to-toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relax one.
All right, eigenvalues and eigenvectors. What are eigenvalues and eigenvectors? Well, let's let A be a square matrix. So A is some n by n matrix, a square matrix of order n. And we have the scalar denoted by the Greek letter lambda, and it's called an eigenvalue of the matrix A. And we also have a non-zero vector, what we'll call X in Rn, if of course X is if A is a square matrix of order n. And it's called an eigenvector of matrix A corresponding to lambda if the following identity holds, and that's A times X equals lambda times X. Now you may look at this initially and say it's a very simple identity. You know, what's so important about eigenvalues and eigenvectors if that happens? Well, yeah, it is a pretty simple identity which is expressed there. But think about what it's saying. So we have three components to this whole deal. We have a matrix A, we have a vector X, and we have a scalar lambda. And we actually take this matrix and we multiply it by a vector, and the answer is simply a scalar multiple of that same vector. Like that's pretty fascinating to me. I find that pretty intellectually stimulating, that I can multiply a matrix by a vector and the result just be a scalar multiple of that same particular vector. So, and again, in this video, we're not going to go into the applications of eigenvalues and eigenvectors. Those are quite important, and we will touch on those in a later video. But today, we're just going to show you how to find it and show that this particular identity holds. So again, it's a very fun thing to do. And one thing I want to mention before I go over how we find eigenvalues and eigenvectors, and it's written in the definition here, but I just want to stress the fact that X can be a zero vector. So it says here a non-zero vector X. So that's saying it can't be zero. But I just want to impress upon that point, because just think about it if X was the zero vector. So, you know, X is a column vector with n number of zeros. Okay, well, A times zero is going to be zero, and therefore lambda has no special. There's nothing special about lambda because lambda could be any number. Any number times zero is going to give you zero. So that's why the vector X has to be a non-zero vector. But however, lambda can be zero. So the eigenvalue can be zero, but the eigenvector cannot. And on our third example that we'll look at, you know, one of the eigenvalues is going to be zero. And I say eigenvalue, so typically there's more than one eigenvalue for a particular matrix. And also there's more than one, in a lot of cases, infinitely many eigenvectors for each particular eigenvalue. So again, a matrix is going to have more than one eigenvalues in most cases, and each of those eigenvalues is going to have more than one and typically an infinite number of eigenvectors. All right, so let's look at the steps of how we find eigenvalues and eigenvectors, and then we'll go through some examples. So how to find eigenvalues and eigenvectors. So we're going to generate something called the characteristic equation. And we generate that characteristic equation by finding the determinant of lambda times I minus A and setting that equal to 0. So again, well, depending on how familiar you are with linear algebra, these vertical bars here, that doesn't represent the absolute value, that represents the determinant, because lambda I lambda times I minus A is a matrix. I is called the identity matrix, and I'll briefly talk about that when I work out some examples. And lambda, of course, is just a scalar of some identity matrix. And of course, I has the same dimensions as A. So I is of order n, and of course A is of order n. So basically, the determinant of lambda I minus A equal to 0 is going to give us a polynomial expression, a polynomial equation, which we call the characteristic equation. The real roots of that characteristic equation are going to be our eigenvalues. So again, this determinant of this lambda I minus A equal to 0 is going to give us an equation which will solve for lambda, the real values of lambda that solve that equation, the real roots. Those are going to be our eigenvalues. And then once we know our eigenvalues, we're going to find the eigenvector corresponding to each eigenvalue. And to do that, it's just another simple equation where you have lambda times I. In this case, it's the particular lambda. So not just lambda, the actual number for the particular eigenvalue. So lambda times I minus A, and that times some vector x equals to 0. And we use that to solve for x, to figure out what x is, to determine the particular eigenvector. So that's the rules. It may not be as lucid as it needs to be, just reading it off, but I guarantee you, as we do some examples, it should become quite clear. So let's go ahead and look at some examples. So here's our first example. Our first example, the matrix A is 7, 2, 2, 4, and we're going to find the eigenvalues and the corresponding eigenvectors for this particular matrix A. Can't wait. Let's do it. All right, so here's our matrix A. And so the first thing we're going to do is lambda times I minus A. And so just briefly, so I of order n is the matrix 1, 0, 0, 1. So basically I, which we call the identity matrix, is a matrix that has ones across the main diagonal and zeros everywhere else. So it's a matrix that has 1 across the main diagonals and 0 everywhere else. So when we multiply lambda by the matrix I, we just have lambda, lambda. So it'll be lambdas across the main diagonal and zeros everywhere. And so basically when we do lambda I minus A, it's going to be lambda minus the numbers on the main diagonal, and every other component of A is going to have a minus, well, not a minus sign, it's going to be the opposite sign because it's being subtracted. So let's go ahead and calculate lambda I minus A. All right, so lambda I minus A is going to be lambda minus 7 minus 2 minus 2 lambda minus 4. And we're going to take the determinant of this guy and we're going to set it equal to 0. Okay, so to take the determinant of a 2 by 2 matrix, what we're going to do is multiply these two minus the product of these two. So if we multiply these two, we'll have lambda squared minus 11 lambda plus 28 minus, those two are just 4, equals 0. So just to simplify those two, this is lambda squared minus 11 lambda plus 24 equals 0. And so that's what we call the characteristic equation. And so we're going to solve for lambda. And hopefully you can see that this is lambda minus 8 times lambda minus 3. So let's say I continue this on another sheet. So if I factor the characteristic equation, I'll get lambda minus 8 times lambda minus 3 equals 0. And so my two values for lambda are going to be 8 and 3. So those are my two eigenvalues. So I'm going to call one lambda 1, 8, and call the other lambda 2, 3. And these are our eigenvalues. So this particular matrix A has two eigenvalues. And so now I'm going to find the corresponding eigenvectors for each eigenvalue. And again, typically it's going to be more than one. And really, in this case, both is going to be an infinite number of eigenvectors. And I'll show you what I mean when I find them. It's going to be an infinite number of eigenvectors for each of these eigenvalues. For this particular example, the first example, I'm going to find an eigenvector for each eigenvalue, at least one. And for the subsequent examples I'll just find an eigenvector for one of the eigenvalues for the sake of time. All right, so let's go ahead and find our eigenvector. So again, how do we find our eigenvector? Well, we do lambda I minus A times x equals 0. Now again, in this equation, this is a certain lambda. So first I'm going to do it for lambda 1. So lambda 1I minus A. Now remember that I is just the identity matrix. You just have ones across the main diagonal and zeros everywhere else. And since it's getting multiplied by 8, it's going to be 8 across the main diagonal and zeros everywhere else. So let me remind myself what the matrix A is. So I'm seeing it here. So I just want to write it for reference. So A was 7, 2, 2, 4. So what we're going to do is we're going to subtract. Well, we're going to do 8 minus the values on the main diagonal, and the other entries in the matrix are simply going to change signs from being subtracted. So lambda 1I minus A would be 8 minus 7, which is 1, negative 2, negative 2, 8 minus 4, which is 4. There is that result there. And then that guy times the matrix, the vector x, which I say has components x1 and x2. That should equal 0. All right, so that's what we have. And so what you'll notice when doing these problems is that this matrix will always be a singular matrix, meaning it's non-invertible. And it has to be non-invertible because this is a homogeneous equation. And if it was invertible, the only solution would be the trivial solution. So the fact that it's non-invertible allows us to find other solutions. So you will notice that this matrix here is always going to be non-invertible. What that means is going to have a determinant of 0 if you're not familiar with that frame. That's one of the things it means. And so if you look at finding the determinant of this matrix, it'll be 4 minus 4, 0. And you'll see that in every one we do, this guy is going to have a determinant of 0. And also, if you look closely, when that's the case, you'll see that this row is simply a multiple of this row. It's this row times negative 2. So when finding, the values for x1 and x2, I'm really only going to use multiplication by this row, because this row really gives me the same thing, just a multiple. So let's go ahead and do this. I'm going to multiply. So when we multiply matrices, this is a vector, but it's a column vector, which is also a matrix. So we just multiply row by column. So 1 times x1, negative 2 times x2, and that should equal 0. So we'll have x1 minus 2x2. All right, so that's going to give us x1 minus 2x2 equals 0. So, or x1 equals 2x2. So what that means is that x1 is going to be twice as much as x2. And so that's why we say we can find an infinite number of eigenvectors for a particular eigenvalue. So there's an infinite number of numbers you can think of that satisfies where the first number is twice as much as the first. We can do 10 and 5, 8 and 4, negative 32 and negative 16, negative 4, negative 2, 150. I mean, we can go on forever, of course. So that's the reason why we said we can, in many cases, there's an infinite number of eigenvectors that go with a particular eigenvalue. So I'm just going to use one eigenvector for this particular case. And so let's say I use the eigenvector 4, 2. So let's say my x is 4, 2. So again, you can see here 2 times x2, this is x2, 2 times x2 equals x1. And remember, for this particular case, lambda 1, what was lambda 1? Was it 8? Yeah, lambda 1 was 8. And so we're going to see if the identity holds. Like, we want to make sure this stuff is true. So we did all this work. So is this identity really true? This identity that a times x equals lambda times x? Like, is that really true? So we're going to see if this guy is actually true. Now, this side of the identity is very easy to understand. And in this case, we're talking about lambda 1 in particular. So we know that lambda 1 times x is going to be 3216. It's quite easy to see. So lambda 1 times x is 8 times x. That's 8 times 4, 2. And 8 times 4 is 32, and 8 times 2 is 16. So that's what we get from this side of the identity. And so if this holds, then a times x should give us the same thing. So let's see if that happens. The suspense is killing me. So let's A. So I remember A. So A was 7224. So A is 7224. That's the matrix A. And the eigenvector x we're using here is 4, 2. And we're going to see if we multiply this, we're anticipating that we're going to get 3216. Let's see if that actually happens. Now, remember, when we multiply matrices like this, and I know this is a vector, it's a column vector, but it's also a matrix. We're going to do row by column. So let's see what happens. So 7 times 4 is 28. 2 times 2 is 4. 28 plus 4 is 32. And now we're on this row. So 2 times 4 is 8. And 4 times 2 is 8. And 8 plus 8 is 16. And indeed, we do get the same thing. And so this identity was indeed approved. All right, so let's go ahead and find an eigenvector for our other eigenvalue. The other eigenvalue was 3. So let's go through that. So again, for this case, we're doing lambda 2, which is 3. And again, what we're going to do is we're going to do lambda 2 I minus a. That matrix times x equals 0. All right, so you know the deal what lambda 2 times I is going to be. So again, matrix A, just to bring it back for reference, 7, 2, 2, 4. And again, lambda 2 is 3. So 3 minus 7 is negative 4, negative 2, negative 2. 3 minus 4 is negative 1. So there is lambda 2 times I minus a, and that times some vector x. I'll call this components x1 and x2. And that guy should equal 0. All right, so apologize for that paper. And so again, hopefully you can clearly see this row is simply a multiple of this row. It's this row times 2, and hopefully you can see the determinant of this matrix is 0. It's non-invertible. It's 4 or minus 4. So all those things we talked about before are still true. So I only need to do the multiplication of one row, really. So say I do this row. Well, and these numbers are a little bit better. So say I do this row. So it would be negative 2 x1 minus x2 equals 0, or 2x1 equals negative x2. So we have 2x1 equals negative x2. So what that means that the value of x1, well, the value of x2 is going to be twice as much the value of x1 and the opposite sign. So kind of somewhat of the reverse of what was in the first case, but also the additional thing is going to be the opposite sign. So one vector we can use to satisfy this relationship. So again, what I want x2 to be twice as much as x1 and also a different sign. So say I use the vector 5, negative 10. And again, if you look, just making sure it satisfies the identity, this is x2, negative x2 is positive 10, and this is x1, 2 times x1 is positive 10, so it holds. So the vector 5, negative 10. So we're gonna see if that identity holds, a times x equals lambda times x. All right, and you know, I don't know if I've said this, but don't you find it quite fascinating that I can multiply a matrix by a vector, and that answer simply be a scalar multiple of that vector? Like, you don't find that fascinating? I find it quite fascinating and also very fun to do. But let's get to the work. All right, so what I want to prove for all my skeptics out there, I want to prove that a times x is equal to lambda 2 times x. I want to prove that for all of my skeptics out there. All right. And since this is a different eigenvector, I guess I could have did a subscript on it, but I didn't. Okay, so let's do a times x. So again, matrix A is 7, 2, 2, 4. And in this case, x is 5, negative 10. And lambda 2 here was 3, right? So we can just look at what we expect this answer to be. We expect the answer to be 15, negative 30, because that's lambda 2 times both these. So we should get 15, negative 30. So let's see if that happens. All right, so we'll have 7 times 5, that's 35. And 2 times negative 10, that's negative 20. 35 minus 20, 15. So far, so good. And then for our second row, we'll have 2 times 5, which is 10, and 4 times negative 10, which is negative 40, 10 minus 40, negative 30. So indeed, we get what we expected to get. All right, so that's one example. And so this example, we looked at a 2 by 2 matrix. I'll do 2 more examples where I'll look at some 3 by 3 matrices, and we're doing this by hand. And so typically, when you're doing this by hand with a matrix of order 3 or above, those matrices tend to be more sparse to let you, efficiently do the problem. And so that means there's going to be, quite a few zeros in the matrix. It just allows us to do those type of matrices by hand in a more efficient manner. And this next example is gonna have an eigenvalue of 0. I think in the beginning I said it's gonna be the third example. It's actually gonna be our second example. So the next example we're gonna look at is gonna have that magical eigenvalue of 0. So we'll kind of see how that looks. All right, let's look at the example. All right, so here's our example number 2, and there you see the matrix there, and it does have its fair share of zeros. Out of 9 entries, 4 of those guys are zeros. And again, that allows us to do this calculation on these bigger matrices by hand fairly efficiently. All right, so let's go ahead and find the eigenvalues and eigenvectors of this particular matrix. All right, here's our matrix. So let's go ahead and find our eigenvalues. So again, we're gonna take the determinant of lambda I minus a, set that guy equal to 0. And so that will give us lambda minus 1, positive 2, negative 1, 0, lambda, negative 1. I don't know why I didn't write the 1 there. So let me make sure I didn't make a mistake, because I just had a minus sign just sitting there. So this is going to be lambda minus 1, positive 2, negative 1, 0, lambda, 0, 0, negative 1, lambda minus 1. All right, so that's lambda I minus a, and we're going to take the determinant of this guy and set it equal to 0. Now, when you find the determinant of a matrix of order 3 or more, you can find that determinant based on any row or column you want. Now, of course, it's always beneficial to use, when you have zeros, to use a row or column with 0. So like column 1 or row 2 would be the obvious choices, because two of the guys there are zeros, it makes the work easier. So I'm going to go ahead and find this determinant based on column 1, since those two are just going to zero out for us. So to find the determinant of this, this would be lambda times 1 times lambda minus 1, and then minus 0. So let's write that. So we'll have, I think I have room to put it here. We have lambda minus 1 times lambda minus 1. So for that lambda times lambda minus 1, since it's being multiplied, I'm going to put a lambda there and a square there, and that's minus 0 equals 0. So there is our characteristic equation there. I think from there it's obvious to see that our eigenvalues are going to be 0. So say lambda 1 is 0, and positive 1, lambda 2 is positive 1. So there is that case where we have an eigenvalue of 0, which we of course have forecasted. So let's find the eigenvector for 0. So again, on this particular example, I'm only going to find an eigenvector for one of the eigenvalues. In fact, that's what I'm going to do on the last two examples. Simply one eigenvector for the particular eigenvalue. So let's see how it works out finding an eigenvector when an eigenvalue is actually 0. See, is it easier? Is it harder? Is it more fun? Is it less fun? Let's see. All right. So to find our eigenvector, and this eigenvector is coming from lambda 1, which is 0. So what we're going to do is we're going to do lambda 1 times I minus a times x equals 0. All right. So lambda 1 times I is simply 0. So basically what we're going to have is negative a. That's what we're going to get to result of that. Where is matrix A? So let me just pull up matrix A for reference. So what we're going to end up getting is negative 1, positive 2, negative 1, 0, 0, 0, 0, negative 1, negative 1. All right. So that's what we get for lambda 1I minus a. And we're going to multiply this by the vector x, who has components x1, x2, and x3. And we want to get 0, 0, 0. All right, so let's do the good work. Okay, so when we do the first row, we'll get negative x1 plus 2x2 minus x3 equals 0. Okay, and then when we do the second one, we really get nothing. And then when we do the third one, we'll get negative x2 minus x3 equals 0. All right, so let's solve this guy the best way we can. So one thing we know, one thing we know is that x2 is going to equal negative x3. That's obvious from here, but let's bring some relationship with x1 into this place. But let's go ahead and state that from this guy here, we can say that x2 is going to equal negative x3. All right, that's been established. So now let's get a relationship with x1. So let's do this guy minus this guy. So let's subtract. We're doing this, of course, to eliminate this x3 here. And when we do that subtraction, we're going to get negative x1 plus 3 x2 equals 0. So that means that x1 equals 3x2, and x2 equals negative x3. So x1 is 3 times as much as x2, and x3 is the opposite sign of x2. All right, so again, we have an infinite number of values we can use, but let's say we use the vector 12, 4. So my x1, 12, is 3 times as much as my x2, 4. And then my x3 should just simply be the opposite sign of x2. So 12, 4, negative 4. That's the eigenvector I want to use. So again, the eigenvalue was 0, but that doesn't mean the eigenvector is going to be 0. I mean, the eigenvector can't be 0. And you can see the eigenvector has all non-zero entries. So just because the eigenvalue was 0, and it really didn't make it easier or harder. It's on the same level we found. Well, maybe it was a little bit easier because lambda 1i minus a was simply just negative a. But other than that, it was pretty much the same. So let's go ahead and see if our identity can be verified. So we're trying to make sure that the following works, and that is that a times x is going to be equal to lambda 1 times x. All right, so, and again, lambda 1 is 0. So let's bring back our x. So our x is 12, 4, negative 4. And lambda 1 is 0. So this side of the identity is going to be 0, 0, 0, obviously. So we're trying to see if this part of the identity also is going to equal 0, 0, 0. All right, so let's bring back what matrix? Bring back matrix A. And matrix A was 1, negative 2, 1, 0, 0, 0, 0, 1, 1. And so we're going to see if this times x, and again, x is 12, 4, negative 4. We're going to see if this gives us 0, 0, 0. Let's see. Can't wait. So let's do the multiplication. So 1 times 12 is 12. And negative 2 times 4 is negative 8. So that's 12 minus 8. That's positive 4 right there. And then 1 times negative 4 is negative 4. You have positive 4 and negative 4 is 0. That one works. Now, obviously, this one you're going to get 0 because you have 0 times all 3 of these. And then the last one, you have 0 times 12, which is 0. You have 1 times 4, which is 4. And 1 times negative 4, which is negative 4. So you have 0 plus 4 times negative 4. That is indeed 0. So that's how it looks when you have an eigenvalue of 0. You can see your eigenvector is still kind of the same deal. It's not like the eigenvector is going to have zeros. As we said, again, an eigenvector is a non-zero vector. All right, let's do one last example. Again, this one will also be a 3x3 matrix. We'll find the eigenvalues in one eigenvector for one of the eigenvalues. All right, so here's our last example. And again, you can see little sparsy there on this matrix. So once again, we have 4 zeros, and I already told you the reason why. So let's go ahead and find the eigenvalues and at least one eigenvector for one of the eigenvalues for this particular matrix. All right, let's get into it, my guys. So you should be familiar with the process. So we're going to run through the process a little more quickly this time around. So again, we're going to do lambda I minus a, determinant of that matrix. Set it equal to 0, and so we do that, we'll get lambda minus 2, 0, negative 1, 0, lambda minus 3, negative 4, 0, 0, lambda minus 1. We'll take the determinant of this guy and set them equal to 0. So what you should see here is we have a triangular matrix. We have nothing but zeros below the main diagonal. When you have nothing but zeros either above and or below the main diagonal, that's a triangular matrix. The determinant of a triangular matrix is very easy to find because it's just a product of the entries of the main diagonal. So the determinant of this matrix is simply going to be lambda minus 2 times lambda minus 3 times lambda minus 1. And that, of course, is going to equal to 0. So you can see here we have 3 eigenvalues, 2, 3, and 1. I'll just use the first one. So I'll say lambda 1 is 2, and I'm going to find an eigenvector for this particular eigenvalue. Again, there's 2 other eigenvalues. There's an eigenvalue of 3 and also an eigenvalue of 1. But I'll just find an eigenvector for this eigenvalue of 2. All right, let's go through that process. So let me just remind myself that the eigenvalue I'm using here is 2. And to find the eigenvector, what I'm going to do is lambda 1 I minus a times x equals 0. And so let me remind myself what a is. Okay, there's a. So I will have 2 minus 2, which is 0, 0, negative 1, 0, 2 minus 3, which is negative 1, minus 4, 0, 0, and 2 minus 1, which is 1. So there is the vector lambda 1i minus a, and we'll take that guy times x with components x1, x2, x3, and we'll set that guy equal to 0, 0, 0. All right, so let's go ahead and solve this one. So this one's guys a little crazy. So if I multiply this first row, these two are going to zero out, and I'm going to have negative x3 is 0. Okay, so that means that x3 is 0. And if I multiply this next one, I'll have negative x2 minus 4x3 equals 0. But remember, x3 is 0. So that's just going to be minus x2 equals 0. So that means that x2 is 0. And now if I multiply the third one, 0, 0, I'm just going to get that x3 equals 0. I already know that x3 equals 0. So x2 is 0, x3 is 0. There's no way to get x1. So x1 could be any number in the universe. So I can choose any number I want for x1. So I'm just going to say, for this case, let's say x1 is 3. Again, it could be any number. Well, I'm going to use 3 for this particular eigenvector. And again, there's an infinite number of eigenvectors. Any eigenvector of the form k, 0, 0 would work. But in my case, I'm going to use 3, 0, 0 for my eigenvector. So again, let's see if the identity holds. So what we're trying to prove here is that a times x equals lambda 1 times x. Lambda 1, again, is 2, and x is 3, 0, 0. Yeah, x is 3, 0, 0. And so I think it's fairly easy to see that lambda 1 times x is simply the vector 6, 0, 0. And so let's see when we do a times x if we get 6, 0, 0. So a again, where's a at? Here's a. So a is 2, 0, 1, 0, 3, 4, 0, 0, 1. That's the matrix A. We'll multiply it by the vector x, which is 3, 0, 0. And we're in hopes to get an answer of 6, 0, 0. Let's see if it happens, folks. All right, so let's go. 2 times 3 is 6, 0 times 0, 0, 1 times 0, 0. We get the 6 up there. So far looking good here. 0 times 3 is 0, 3 times 0 is 0, 4 times 0 is 0. Looking good. And here, 0 times 3 is 0, 0 times 0 is 0, 1 times 0 is 0. We do indeed get the matrix 6. Give me the vector 6, 0, 0 as projected. And from this multiplication, you can clearly see that I could have used any value for x1 here, because really the only number that we're getting here is this number times 2. And again, that's the value of lambda 1. So, whatever value I put here, say I put a 7 here, then that means I have to get the vector 14, 0, 0. And again, if that was a 7, it would have been 7 times 2, and the d would get to 14. So that's just another indication that, again, I could have put any number I want at x1. All right. So that's going to conclude this particular lesson on eigenvalues and eigenvectors. I hope you enjoyed it. I hope you understood it, and we will see you next time.
Specialized in science and math, original black men, busting thoughts that pierce your mental, the fierce, ripping your section, vocal toe to toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relaxed one.